Hi everyone, this is Muhammad Musharraf. We are from Gokuraju Rangaraju Institutes of Engineering and Technology. So our final year major project is design and development of high frequency inverter for wireless power transfer applications. So as you know, wireless power transfer technology is day by day increasing, and for the demand for WPT technologies has increased due to many reasons. And in wireless power transfer technology, inverter play a crucial role as a wireless power transfer depends upon transferring energy inductively from one coil to another coil, which required high level of inductance. For that we need high frequency. There are many advantages of using high frequency. Among them are size of the components will increase and the value of the inductance will be increased. With a less amount of components you can produce more amount of inductive value inductance. So what we have done is, in the last sem we had our project aim is abstract is to design 90 kilohertz high frequency inverter. For that we had validated and designed a MATLAB model in the last sem with different operations and with the different switches, with the open loop and closed loop operations, with the different types of topologies. And this is our last this is the closed loop operation with the PI controller and many topologies we had designed. And next, in this in this last phase we have developed a hardware prototype model which will produce 230 volts 90 kilohertz output. We had used R loads at present, and we had studied the behavior and comparison of in software, what we have done in simulated and what is our hardware results. And this is the block diagram. It is little bit simple. There is no complexity in this. So we had generating a triangular pulse, high frequency triangular pulse, and we are giving a reference wave which we need a 90 kilohertz, and low pulse width modulations will be generated which will be given to H bridge. And depending upon the turn off and turn on of MOSFETs, output will be produced. This same exact this model we had used in simulation. We had used H-bridge, and we had take proportional integration feedback and so on. And this is the supply which we use normally, DC supply. And this is the hardware schematic diagram which we had developed. So we had used as a battery for DC source. Without battery we also use SMPS or RPS. And this is the high frequency inverter part, and this is the load. We are going to take the voltage and current feedbacks from the load sides, and we are using a controller which is MSP multi-signal processor, MSP 430 and G2 series. In this we are converting current voltage and current sensors into digital signals, and we are generating PW at high or low, and we are giving this signal to the driver circuit which will generate pulse width modulation signals, and it will give to gate terminal of the MOSFETs. And we are respectively using LCD to display the voltage and current levels simultaneously. And these are the hardware components which we had used. We had used 12 volts 1.3 ampere hour battery, and at beginning, and after that we had used 12 volts 7.5 ampere hours for better due to multiple times of charging and discharging. We had used a better battery, with a higher power. We had also used SMPS for continuous iterations, and regularly we had used for inversion converting switches. We had used MOSFET IRF Z444N and MSP controller and ZMCT103 current sensor. It is a current sensor. It will measure AC and it will work on the Hall effect. And ZMPT101 BAC AC voltage sensor. It will just like a step down transformer with a potentiometer which will adjust and will give output 0 to 5 volts high values. Both sensors give 0 to 5 volts. I mean, depending upon these, we can stabilize the our required readings from it. And load, we had used bulbs and some remaining component connecting words. And for developing pulse width modulation, we had used SG3525A, which will generate I mean pulses for the MOSFET gate terminal. And LCD for I mean displaying the current and voltage values. And PC187 photocoupler, this is we had used to isolate the inverter from the I mean MSP controller. I mean further I will explain about it. And Arduino Nano, we had used Arduino Nano due to I mean our MSP controllers analog pins are not working properly. I mean working properly, but they are not giving a exact result. So for that we had used Arduino Nano. And this is our circuit diagram. What we have done, what we have used. This is our MSP, and this is Nano, and this is a PWM SD3525 circuit diagram. The connections, and this is voltage sensor, current sensors, and LCDs. And from this, at the beginning, we will supply 12 volts supply to buck converter. Buck converter will convert 12 volts into 5 volts, 5 volt DC. As it is all components works on all electronic components, maximum works on the 5 volt supply. As MSP, Nano, and sensors, everything is 5 volts supply. So we had used a buck converter. A 12 volt DC supply is converted into 5 volt DC supply through LMN25965 buck converter. The 5 volt supply is connected to variable electronic components such as LCDs displays, voltage and current sensors, MSPs, and nano controller, with which operated obviously at 5 volts DC supply. Simultaneously 12 volt supply is given to inverter circuit, is here inverter circuit, as well as center tapped ferrite transformer, as it is a 12 0 and 12 volts transformer. Okay, further it is given to Arduino Nano. I want to explain it from the backward as a reverse engineering technologies. So what happened, we will take voltage and current sensors feedbacks, and these feedbacks we will give to Arduino Nanos A0 and A1 input pins, which is used to convert analog signal into digital signal. And these digital signals D5 and D6 pins is of the voltage is given to level shifter, as a MSP works on the 3.3 volts. So we want to convert 5 volts supply into 3.3 volts. So we had used a level shifter. And then output of the level shifter is connected to P10 and P1.1 of MSP. MSP is interconnected with LCD displays, which will display the measured value of current and voltage for monitoring all data. Simultaneously, we will stabilize. We will write a program that will stabilize the and fractionize the input values of the voltage and current sensors, and will produce a readable output display in LCD, as well as generate a high or low pulse for the SG3525. And it will generate pulse signals depending upon the feedback values. The output of MSP pin P2.4 and P1.6 to PIC816 in optocoupler. This is the optocoupler. Optocoupler is used to just isolate the MSP from the inverter, and that is the main purpose. Okay, used to give. I see it also help prevent backflow of power, which will damage MSP while performing iterations. And these signals will be given to the here optocoupler, and from this we had given to VCC and S0. Okay, and on receiving signals from to SG3525 from the MSP through optocoupler to VCC and S0, it will generate PWM signals of high frequency, which field is given to IRFZ 444 and MOSFET gate terminal. And switching of the MOSFET, at a higher frequency, 4 times of the switching fundamental frequency, it will generate a frequency of 90 kilohertz. 90 kilohertz, as which frequency we had required. And from the MOSFETs, we are using high voltage, I mean transformer to convert 12 volts into 230 volts as our load requirements. We had used in between, we had used many filters to reduce the noise levels. We had used a ferrite transformer 12 to 230 volts at a ratio of 9.6 and 9.4. Finally output of the transformer is connected to the load. This is the working model of our inverter. You can see in this video. See, this is our load, and this is the transformer. This is the LCD display. This is voltage sensor. This is current sensor. This is inverter part, and this is LCD, which will display the current and voltage values. And here we are, while performing iterations, we had used an SMPS. It is 12 volts, 15 amperes. SMPS as a charging of battery will take a lot of time, so we had, while performing iterations, we had used this. And this is that. And next, this is the output waveforms of our inverter part. See, this is the output at approximately 230 level. Due to, I mean, we had used filters. It is a square, and with a high levels, I mean, level of noises and irregularities. It will due to some electronic constraints. If you use a 12 volts 1.3 hour battery, it will generate 230 volts at 30 kilohertz, approximately 30 kilohertz. As there are, as we switch on the supply, voltage of the transformer will decrease, and as we had used a 12 volts 1.3 hour battery, it will give little power for some, the power for little time. So frequency is generated at 30 kilohertz approximately. If we use SMPS, we will get 120 kilohertz of frequency, due to, as SMPS will supply constant voltage, and we are using 15 amperes while switching MOSFET. That will current causes high level of switching, which will simultaneously generate high frequency. And this is also our working, our hardware model. This is inverter part. This is our load. This is current sensor, voltage sensor. This is battery. This is buck converter. This is Arduino Nano. These are all connecting wires. This is MSP. This is voltage level shifter. These are the all parts, hardware parts. We had connected 100-watt bulb, as our ratings of the inverter is 100 watt. We had connected 100-watt bulb, and this is what we had done. And so we had in this project we had generated 120 kilohertz with SMPS and 30 kilohertz using a battery. So our main purpose is what we have generated. Our output readings are, if you are connected our output to the compensating coils or coils, it will transfer power, and it will, without wirelessly transfer power. So our outputs are required requirements for the wireless power transfer before compensating coil. So I will conclude that we had up to such level successfully completed our project, and thank you for listening patiently.